Hey guys, welcome to section 3.7. We're going to be looking at some word problems today. And we're going to see how we can use the derivative to help us solve rate of change problems. And we're going to be focusing on the natural and the social sciences. Okay. So there you go. So what are some things that we know about the rate of change? Well, let's suppose we have a function like y equals f of x. We know that if we take the derivative of that function, so like y prime, f prime of x, dy dx, df dx, right? Potato, potato. This is a rate of change. The derivative is the rate of change. When we're talking about the slope of a tangent line, that's the derivative, right? And slope is rate of change. So all of these things are related. So, and in our Leibniz notation, it's rate of change of y with respect to x. WRT with respect to x. All right, so in application problems, when we're talking about dy dx, we have to remember that when we state our answer, because normally with word problems, real life applications have units, like how we measure area is like square feet. How we measure a distance could be miles. So when we're finding the units of the derivative, we're going to be looking at the unit of y per the unit of x, or over the unit of x. Okay, so this is going to be helpful when we're stating our solution in this section. And just to give you an example of a unit of rate of change, you know, when we fill up our car with gasoline, we talk about the miles per gallon, how many miles we get for each gallon of gas. And that's a rate of change. So it looks like miles divided by gallon, but we say miles per gallon. All right, so those are the kinds of things we're going to be talking about today, those kinds of rates of changes. How do the miles change for each gallon of gas? All right, so we know, let's kind of do a nice review for ourselves again, that the average rate of change, we're not talking instantaneous velocity, we're talking about the average rate of change. So going all the way back to the beginning of our semester, we were looking at the change of, well, we would say the change in distance over the change of time. Remember, for average velocity. So now doing average rate of change, we're going to make it more general to any type of problem, not just a distance time problem. And it's going to be the change of y over change of x. And we saw that this can look like, you know, f of x2 minus f of x1, for instance, over x2 minus x1. All right, and then in calculus, we started talking about the instantaneous rate of change. All right, so no longer over an interval of time. What happens in an instant? And we can find that using derivatives. So something like dy dx. Okay, and we've also seen some examples where we look at the average rate of change and how we turn that into the instantaneous rate of change. We let delta x, this interval, get closer and closer to 0. So we've had a limit definition of the instantaneous change as well. All right, so this is all kind of a nice review of what we're going to need for this section. Okay, and then final review before we look at a problem is let's remind ourselves what the S function stands for, like S of t, for instance. And we can just, again, it's some function of t, so we'll write S equals f of t. That stands for our position function. So it tells us where an object is relative to time. And what happens if we take the derivative of the position function? All right, so if we take the derivative of the position, it's the rate of change of the position versus time, which is exactly what velocity is. All right, and then if we take the derivative of velocity, we're asking how fast does the velocity change? Well, that's exactly what acceleration is. Okay. So this is how we're going to be using our derivatives. And we're going to first turn to number 3 in your homework set. It's a big problem. It's so big I actually made a PowerPoint because it's just a massive amount of information. So let's see what number 3 says. So we have that a particle moves according to a not law of motion, but law of motion, S equals f of t, where t is greater than or equal to 0, and t is measured in seconds, and the position s is measured in feet. Okay, so they say what the function is. Sine of pi t divided by 2. Okay, so look at all we have to find. First, we're going to find the velocity. Okay, so let's start there because there's a ton of things to do right now. Okay, so part A. Well, let me write down our position function. And it's sine of pi t over 2. Okay, so part A, we want to figure out the velocity function. And we know that the velocity function, we just have to take the derivative of the position function. So that one's straightforward enough. So again, velocity function, you can say it's either f prime of t, or you can think of it as s prime of t. Oh, I switched colors twice. Okay, so we have to take the derivative of that sine function. That's what this is telling us to do. And it looks like we're going to have to use a chain rule because the outside function is sine and the inside function is pi t over 2. And if it helps, we can really separate the coefficient, the constant, from the variable t. Okay, so now we can clearly see what the coefficient is, pi over 2, and then the variable is just t. All right, so then the velocity function, we take the derivative of the outside function first. What's the derivative of sine? Cosine. Inside function stays there. All right, and then we take the derivative of the inside function, and let's see, the derivative of t is just 1. So 1 times pi over 2. Okay, and I like to put the constant in front. So I'm going to say that this is our derivative, our velocity function. So there you go. All right, so far not so bad. Let's see what the next part is. We want to know what is the velocity after 1 second. So that means after 1 second, our t is going to be equal to 1. All right, so let's look at part B. After t equals 1, okay, we're going to plug in v sub 1 to figure that out. Okay, so v sub 1, I'll switch colors so You can see the difference. It's going to be equal to cosine. Let me rewrite that. I was looking at the function above, but it's the one all the way over here. It's going to be pi over 2 times cosine of pi over 2, and then t is 1. So it's just pi over 2 times 1. Okay, so what's the velocity after 1 second? Well, cosine of pi over 2 is 0. So the velocity is 0. Okay, so that's interesting. But remember, this just means that at this time, the function is just at rest. All right, and if you wanted to do just a quick sketch, very rough sketch. I'm not even really going to include a scale, but our position function is sine of pi over 2t, right? And time is always greater than 0, so we'll just focus on this part. Okay, so it looks like this, and it goes on forever, right? This is s. And then your velocity is cos pi over 2 cosine pi t over 2. So we're looking at something like this. All right, and again, it's forever. So what happened is at this moment right here, after 1 second, our particle is, at rest. There's no velocity right now. And then looking at our position function, normally no velocity happens when we change direction, right? When we're going one way and then we're changing directions. So we're probably at a peak at time equals 0. All right, tally ho. Oh, I'm sorry. Let me get some units in there. I shouldn't just say 0. We should say 0. And then what was our question? Let's refer back to the units. 0 feet per second. So write 0 feet per second. There, that's a better answer. All right, so let's move on to part C now. I'll switch colors so we know it's a new section. C, when is the particle at rest? Well, we found one instance. We know the particle is at rest at t equals 1 second. Let's figure out where else it's at rest. So the particle is going to be at rest when the velocity is 0. So we're going to be at rest infinitely many times, right? And again, this goes on forever because time goes on forever. Okay, and again, that's going to our position function wherever we switch positions, going from a positive rate of change and then going backwards, having a negative rate of change. Okay, so we would want to know, when is the particle at rest? The particle is at rest when your velocity function is equal to 0. So our velocity function is, again, pi over 2 cosine of pi over 2t. So when is that equal to 0? All right, well, let's divide. We can divide both sides by pi over 2, right? And 0 divided by pi over 2 is just 0. So really what's making the left 0 is that second factor. So we want to figure out when the cosine of pi over 2 times t is equal to 0. Okay, so how we're going to do this, and maybe you know how to solve this using trig, because this is really just a trig problem at this point. Let's consider our unit circle. And again, we want to figure out where the cosine is 0. And the cosine is 0 when we're at the y-axis, when the unit circle intercepts the y-axis. So we want to figure out, and remember, it oscillates forever, right? It goes around and around in circles. So we want to find all values of pi 2 over t where we're going to be intersecting the y-axis. Okay, so we know that this is pi over 2 on the unit circle, and this is 3 pi over 2. And then if we go around again, let's see, this is going to be 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2, okay? So essentially what we're doing to get these two angles is we're taking pi over 2 and we're adding half a rotation. All right, so half a rotation is pi. And to indicate that we do it forever, we're going to do it times k, where k is a constant. So going back to our problem, we're going to want this argument, pi over 2 times t, to either equal or to equal this expression, pi over 2 plus pi k. So when is our argument equal to this expression? Because that's when we're going to land at the x-axis, or excuse me, the y-axis. All right, so we are essentially solving this for t. So what would we have to do to solve this for t? To figure out the times that we're at rest, let's get rid of this coefficient by multiplying both sides by 2 over pi. Okay, that's going to cancel that to 0. And then whatever we do to one side, we do the other. And then we multiply all terms by that. So what are we left with? So when is the particle at rest? When t is equal to, let's see, this is going to cancel pi over 2 times 2 pi times its reciprocal, so it's going to be 1. Plus, and let's see, over here, our pi's will cancel, and we'll be left with 2k. All right, where k is an integer. So this is when is the particle at rest? At 1 plus 2k. 1 plus 2k. What does that look like? Well, first of all, just something to help me make sense of this formula. What it reminds me of is the formula for an odd number. So a little thought bubble. An odd number, how we write any odd number is it's a multiple of 2 plus 1. So it looks like t has to be an odd amount of seconds. All right, and a couple other things. We know t has to be positive. T has to be positive. It has to be greater than 0, greater than or equal to 0. So when we're talking about k, k is just not any integer. It has to be a positive integer or greater than or equal to 0. Because if k was -1, then our t would be what? 1 minus 2 be -1 seconds. That's not possible. So we can make a little note right here. K has to be greater than or equal to 0 and an integer. All right, and the reason why k is an integer just came from our graph up here, right? When we were figuring out what was going to land us on the pi over 2 and 3 pi over 2 mark. All right, so t is an odd integer, right? That's essentially what this is saying. T is a positive odd integer. So to see what kind of values we're looking at for t, let's plug in k equals 0. And we're going to get what? 1. What happens when k equals 1? 3. What happens when k equals 2? 5, 7, 9, dot, 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 continuing forever. And these are the seconds. All right, so now we know where the particle is at rest. So going back up to our very, very rough sketch of the velocity, all of these little marks right here are the odd seconds. Okay. Let's see what else we have in store. Let's look at part D. Part D. When is the particle moving in the positive direction? When is the particle moving in the positive direction? Okay, well, let's examine this. So when is the particle moving in the positive direction? So that would be when we have a positive rate of change, right? When we're increasing, that's our positive rate of change. So for part D, when is the particle moving in the positive direction? When we have a positive rate of change, when our function's increasing. So those are all the moments where our velocity is positive. All right, so we're going to consider all of that yellow region. And actually, you know, because we have this nice picture, we can kind of tell where we're going to be moving in the positive direction. But let's also solve it using calculus, just in case we weren't able to sketch out the nice velocity function, because that's definitely a possibility. Maybe the velocity function is so complicated we can't make a sketch. So we're going to have to know it doing calculus too. So let's look at that solution. So part D, when is the particle moving in the positive direction? So positive direction, because think about it, when you're, you know, just walking, you can walk forward or you can walk backward, right? So forward would be the positive direction, walking backward would be the negative direction. So we're moving in the positive direction. So like walking forward, for instance, not walking backwards. We would have a positive rate of change. So where our position function is increasing and our velocity function is positive rate of change. All right, so over here, this would be like an increasing S of t, whoops. And that would correspond to a positive velocity, okay? All right, so let's hop to it. Well, we know our f prime function, we know our velocity function, the derivative of the position. It's pi over 2 cosine pi over 2t. And we want to know when that's greater than 0. All right, well, kind of the same process as last time. Let's divide both sides by pi over 2, which is a positive number, so our inequality sign won't change. So we want to know when the cosine of pi over 2t is greater than 0. So just like last time, oops. We want to know where the cosine is positive. Okay, and the cosine is going to be positive. Let's see, cosine is the x value, so quadrant 1 and quadrant 4, right? That's where our x is going to be positive, so that's where our cosine is going to be positive. And just as before, let's think of that in terms of angle, right? So what argument of cosine are we looking at? Let me do a range, right? So a whole interval. So I'm going to start at negative pi over 2, and we're going to go all the way up to pi over 2. All right, and then that's just one rotation. Then we go on another rotation to 3 pi over 2, and then 5 pi over 2, then 7 pi to 9 pi, etc., etc. So I'm going to add rotations, multiple rotations to those two numbers. So we're going to be adding 2 pi over k. All right, but it's not just the angle. Well, it's the argument. This is what we want the argument of cosine to be. So now we have to consider that our argument over here is pi over 2 times t. So whatever this argument is right here, it's going to be ranging from this value to this value. So it's going to be looking like this. So negative pi over 2 plus 2 pi k. It's going to be less than the argument of our cosine function, and it's going to range all the way to pi over 2 plus 2 pi k, like that. And then we're going to want to solve it. This is a 3-part inequality, and we're going to want to solve it for t. So if you remember our strategy for three-part inequalities, we isolate the variable in the middle. So we're just going to get rid of that coefficient, pi over 2. So that's like multiplying everything by its reciprocal. Okay, so, and look at multiplying all three parts of the inequality. After we distribute, it's like multiplying each term. So we have to multiply 1, 2, 3, 4, 5 terms by 2 over pi. All right, so let's do that. So over here, that's the reciprocal. So -1 plus, let's see, here the pi's will cancel. 2 times 2 is 4. Okay, and that's going to go to t, because that's how we designed it. Again, here we're multiplying by the reciprocal, so we're left with 1 plus the pi's cancel. 2 times 2 is 4. And there we go. Okay, so remember, our time is going to be positive. Time has to be positive or 0. So let's think of the values of k. So for instance, k couldn't be -1 because that would give us a negative time, right? That'd be like -5 to -3. That's not helpful. If k is 0, this would be -1 to 1. And that kind of works, okay? So let's start seeing this pattern because it looks a little confusing right now, right? So let's plug in some values of k to see what's happening. When k equals 0, we're going to get that the time interval is going from -1 to 1 second. And let's see, we can't be -1, but we can be 1. So where does t start in a where does the time start in a situation? Time starts at 0. So we'll just move it to 0. All right, so there you go. So the first period where the particle is moving in a positive direction, we're looking at 0 to 1 seconds. And then what about the next? Well, k is an integer, so we're going to go to 1. And when k is 1, let's see, -1 plus 4. And when k is 1, it's going to be 1 plus 4. Okay, so it's 3 to 5 seconds. And when k equals 2, we can do this forever, right? If k equals 2, it's going to be -1 plus 8. When k is 2, it's going to be 1 plus 8 seconds, etc., etc. So, you know, just kind of continuing this pattern, it's going to be on this interval, just like we said above, where k is greater than or equal to 0 and an integer. That's where we're going to be moving in a positive direction. And if we go back up to our very rough sketches of the position function and the velocity, that's exactly what we have, right? We have 0 to 1, 3 to 5, 7 to 9, 11 to 13, etc., etc. So those were these intervals right here, 0 to 1, 3 to 5, positive direction, we're increasing, etc., etc. Okay, so, and if you want, we can even put in these marks here now because now we know them. 3, 5. All right. Good. So I'm really getting to know our graphs right now. Let's see what's next. Let's see what's next. We're on part E. Okay, find the total distance traveled during the first 6 seconds. The total distance traveled during the first 6 seconds. Okay. This one is interesting. So let's go up. Total distance traveled, that sounds like a position function to me, okay? And now the thing with the total distance traveled is this is our position function, okay? And notice that we have a lot of zeros, right? And because that, listen to the reason why. So we go in the positive direction, so we walk forward, and then we walk backwards to the same spot. So the displacement is 0, right? We're back where we started. If we walk forward and then walk back to where we started, the displacement's 0. But that doesn't mean we didn't walk any, right? We walked up maybe like 10 feet, and then we walked backwards 10 feet. Okay, and so it's really, we walked 20 feet, but the displacement looks like 0. So if we wanted to find the total distance traveled in 6 seconds, we can't just plug in S of 6. We can't just plug in S of 6 and subtract S of 0, because to me it looks like S of 6 is going to be 0. So the displacement at 6 seconds is 0, but how much did we travel? So we're going to actually have to find the distance along the curve. So how are we going to find the distance traveled along the curve and not just the displacement? All right, so let's write some of those thoughts down. Let's write some of the thoughts down. Okay, so we're on part E. We want total distance traveled. The total distance traveled during the first 6 seconds, which is different than what S of t gives us. S of t just gives us the displacement, the distance from the origin. So how far are we from our original spot? Not the total distance traveled. So here's what we're going to have to do. Okay, so first of all, here's our position function. We call it f in this problem. It's sine of pi t over 2. Okay, and we know that we go in a forward direction when our graph is increasing, and we go in a negative direction, so like walking backwards, when our function is decreasing. Okay, so we're going to have to consider 2 different scenarios. All right, so from our last problem, we knew that we are moving forward from 0 to 1. It's right here, right? 0 to 1. 3 to 5, we are moving forward. So this is going to be 3 to 5, we are moving forward. And then 7 to 9, we are in a positive direction. And then, the pattern continues forever. Okay, so we're going to have to calculate the displacement for each one of the intervals. So for this one, we're moving forward. And that happens, and I'm going to use this notation now, S of 0 or F of 0. You can use either one. But we can say S of 0 and then S of 1. And then we can actually look at that displacement because we're just moving in one direction. It's a starting point and an ending point. And we don't, circle back. We never walk backwards. So we can actually look at the displacement. Since we're just moving in one direction, the displacement is the total distance. Okay, so since we're moving in one direction, since we're not circling back around, the displacement is the total distance. All right, so let's do it. S of 0, that's going to make this whole thing 0. What's sine of 0? Well, we can see it. It's going to be 0. Okay, and then sine of 1, it's going to be pi over 2. And we can see it too, right? This is a sine function. Sine of 1 is going to be 1. All right, so what's the distance traveled? It's going to be 1 And what are the units again? In terms of feet, right? So we traveled 1 foot in the first interval, 0 to 1. All right, and then when we're moving backwards, this time we start at s of 1, and moving in one direction, we go all the way down to s of 3. All right, and then we can definitely plug in t equals 1 and t equals 3 here, but also graphically we can see that that's at 1. Just how this graph works, right? That's how the sign works. And -1. So what's the distance traveled from 1 to -1? Well, distance traveled is subtraction, right? So 1 minus -1 is 2, right? And on the flip side, we can also look at -1 minus 1 is -2. But since we're talking about distance traveled is positive. So we traveled 2 feet in that time interval. All right, and then once we go from 3 seconds to 5 seconds, we're back in a positive direction again. Okay, so let's see, s of 3 is -1, and then our position function is going to take us all the way to 1. So what's the distance traveled if we go from -1 to 1? Again, that's 2 feet. And then where are we going? It just is 0 to 6, right? Excuse me, 5 seconds to 6 seconds. So again, in a backward direction, the problem told us just to go to 6 seconds. So make sure we pay attention to that one. In 6 seconds, that's the 0, right? We can also plug it in here. 6 divided by 2 is 3. 3 pi, sine of 3 pi is 0. All right, and we see that s of 5 is starting at 1. So how many feet did we travel going from 5 to 6? T equals 5 to t equals 6? 1 foot. So what was the total distance traveled? So not the displacement, but the total distance in 6 seconds is 1 plus 2 plus 2 plus 1. Or 6 feet. All right, and again, if we were to look at displacement, if we start at time equals 0 and we end at 6, right, that's the displacement 0. We're back where we started. And if you just think of, the unit circle, we go forward and we go backward. We go forward and backward, forward and backward. So there's some times where you just end up where you started. So the displacement's 0, but you could have gone around the circle 10 times and traveled a lot and done a lot of walking. But if you end up back where you started, the displacement's going to be 0. The total distance is the distance around the circle each time. All right, so that's fun. So if you look at the next part, we're going to draw a diagram to illustrate the motion of the particle in those first 6 seconds. So let's check that out. Okay, so goodness, where are we? Part F. This is a long problem, right? We're going to draw a diagram to illustrate the motion. Okay, and again, this is our sign function. This is our position function. Our distance, because of it's a sign function, we're only going from -1 to 1. Okay, and we're just oscillating back and forth. So when we draw our diagram to illustrate motion, not position, but motion, again, we're going to be oscillating our position function. I'm going to draw it a little bit lower, actually. Our position function is going to be oscillating between just -1 to 1. Okay, and we start, where do we start? We start at time equals 0. And at time equals 0, what's the position? It also happens to be 0. Okay, so let's start. So here's time equals 0. It's going to be kind of like a 3D graph. And I'm going to mark the spots. This is time equals, let me get a smaller, time equals 0, and your position is 0. It's our starting point, okay? And then what happens? We go in a positive direction until we hit 1 at 1 second. So I'm going to draw us going to, and arrows to say the direction. And at time equals 1, our, oops, that's confusing. All right, second. At time equals 1 second, our position is 1 foot. Okay, I think I'll leave out the units, just, or else it's just going to get crazy. Okay, and then after 1 second, what happens? We go backwards, and we go backwards all the way to -1, and that takes us to time equals 3 seconds. So our position function is going to go back. We're going to circle around, and we're going to go back to -1. And again, we can draw arrows to show distance, or excuse me, motion, direction. And this is time equals 3 seconds. And at time equals 3 seconds, the position is -1 feet. All right, and then what happens? We switch direction, right? We start going forward, and we move forward all the way to 1, and we get to 1 by t equals 5 seconds. All right, so we switch direction again, all the way to 1, and we get there at 5 seconds. So at t equals 5, s is back at 1. Okay, and then we ended at 6 seconds. Oh, let me do arrows to show direction. And then we ended at 6 seconds, and 6 seconds brought us back to 0. So at time equals 6 seconds, the position function was back at 0. All right, and that is an example of a diagram of motion. So now we see exactly how our particle is moving. And essentially, whoops, you know, I'm drawing layers to be really clear about where the motion is. But really what's happening is this particle is just, you know, going back and forth. And then this is showing the motion. Okay, whoopsies. All right, let's see what's next. Part G, find the acceleration at time t and after 1 second. Okay, well, what do we know about the acceleration? F, goodness, where are we? We're at G. Okay, so what do we know about the acceleration? Well, we know that the acceleration is the rate of change of velocity, right? So it's v prime of t. So the velocity function, we've found that. The velocity function is pi over 2 cosine of pi over 2t, or pi t over 2, potato, potato. And so the acceleration is going to be the derivative of that. All right, so we have a constant. Remember, we can kind of ignore the constant till the end. And now the derivative of cosine of pi over 2t, we have to use the chain rule again. So what's the derivative of cosine? That's our outside function, negative sine. And then what's the derivative of your inside function? Just pi over 2. Okay, so we can clean that up a little bit, and then the acceleration function, so that's the first part. What's the acceleration at time t? Let's see, 1 negative sign, so the negative sign will still be there. Pi times pi is pi squared, and then 2 times 2 is 4, and then sine of pi over 2t. So there you go. And then second part of G part 2, is we want to know the acceleration at time t equals 1. So wherever we see a t, we're going to put a 1 there. So pi over 2 times 1, which is just pi over 2, right? What is the sign of pi over 2? It's just 1. So the acceleration is negative, oh goodness, pi squared over 4. And then what about the units? What about the units? Well, let's do a little thought bubble. So acceleration is the derivative of the velocity, right? dv dt. And we can figure out the units by looking at the units of dv dt. So what are the units of velocity? In our case, it's feet per second. So that's the unit of the top. And then what's the unit of dt, or what's the unit of time? Seconds. Okay, and if you clean that up, you can do a couple things. You can multiply top and bottom by seconds. The units of acceleration are going to be feet per second squared. So that's the unit of a of 1. It's negative pi squared for feet per second squared. Okay, and then bonus round. So that's the answer, right? We need units. So we can figure out the units by looking at how we find acceleration, which is dv dt. Second up, why is the acceleration negative? And it's negative because we're slowing down. It's negative because we're slowing down. And let's go back. And that was at 1 second. And if you look at that, we can see we're slowing down, right? When we're coming up, our velocity is the slope of the tangent line, or it's the rate of change. And we're slowing down, slowing down, slowing down until we're 0, okay? And then when we're talking about acceleration, I'm going all the way back. I'm finding my velocity function. All right, here's the velocity function. And the velocity, the derivative of velocity is the acceleration. So the acceleration is the rate of change of the velocity. It's the slope of the tangent line. And if we look at this tangent line right here, it's negative. So the slope will be negative. And again, the slope of tangents of the velocity is the derivative, which is the acceleration. Okay, so that's why we have a negative acceleration. We're slowing down. Okay, so where does that lead us? Whoosh, this is a long problem, isn't it? Okay, so that kind of talks about the next problem, the final part of this problem. When is the particle speeding up and when is it slowing down? So we kind of just introduced that concept, right? So part H. Let me do purple. Okay, part H. When is the particle speeding up? And when is the particle speeding or slowing down? Okay, so it's speeding up when the acceleration is positive. And it's slowing down when the acceleration is negative. But we'll focus first on the positive. Where is it speeding up? So if we wanted to solve this, let's bring back our acceleration function. We just found that in that previous problem. All right, and then let's divide out by the coefficient. But notice when we divide out by the coefficient, we're going to be multiplying by negative 4 over pi squared. We're going to be multiplying by the reciprocal, but the reciprocal is negative. And what happens to an inequality sign when we multiply by a negative number? It flips, okay? So 0 divided by the reciprocal is just going to be 0. But what's going to happen is because the reciprocal is negative, our inequality direction is going to flip. Okay, so now we want to know when the sign is negative. So we can always bring back Mr. Unit Circle to help us figure out where the sign is negative. Sign is the y coordinate, so y is negative down here. Okay, so we're going to be ranging from pi to 2 pi, and then all multiples of that, right? Because we can go round and round the circle. So to add multiple rotations, that's like adding 2 pi k. Okay, but our argument isn't just like t. Our argument is pi over 2t. So we're going to want pi over 2t to fall in this range. So we want pi over 2t to range from pi plus 2 pi k all the way to 2 pi plus 2 pi k. Okay, so let's write that out. Okay, and then of course we solve in a similar way. What are we going to multiply every single term by? 1, 2, 3, 4, 5. The reciprocal of pi over 2. All right, so what are we left with? We're going to be left with 2. Pi's cancel here. All right, and then on the right, pi's are going to cancel. And again, the pi's are going to cancel. All right. So there you go. So speeding up where? So we can write out some intervals just to kind of get an idea of what's going on. So we're going to be speeding up between, let's see. Well, if k is equal to 0, we're going to be speeding up between 0 and 4 seconds. K is equal to 1. Let's see, 2 plus 4 to 4 plus 4. If k is equal to 2, let's see, then 4 times 2 is 8. 2 plus 8 is 10. 4 plus 8 is 12. All right, and then we can generalize it, ... So 2 plus 4k, whoops, to 4 plus 4k seconds. Whoops. There you go. And then we could do something similar for slowing down, right? Slowing down, we would want it to be just the opposite. So we'd want it to be on the upper half, right? So if it's not slowing down, it's speeding up. So essentially, it's just going to be the space in between our intervals. So you guys can definitely repeat the whole process, you know. And then in this case, I'll write in blue to coordinate. You would want, let's see, this would start at like 0 plus 2 pi k. And then the argument is pi over 2t to pi plus 2 pi k. All right, so very, very, very similar. Go ahead and try it on your own if you'd like. But essentially, it's just the in-between spaces. So we would be slowing down then, however you want to think of it, either from starting from scratch and calculating it from scratch, or by looking at your acceleration intervals and realizing if you're not slowing down in this case, excuse me, if you're not speeding up in our sine curve, you're slowing down. Okay, and that's because our sine curve, it's, you know, either we're slowing up or we're slowing down. There's no pauses in the sine curve. All right, so 0 to 2, 4 to 6 is between 8 to 10, etc., and then seconds, of course. Okay, good. And I believe, is that the last part of that problem? It's a ginormous problem. So that's that problem. We still have 2 more questions to go over, but let's do that in part 2 of our video.